Hello friends, here in this video we will see a problem on SFD and BMD for cantilever beams. Here is the question. It is mentioned that draw SFD and BMD for the cantilever beam as shown in figure. The diagram of the beam is given to us. Now I'll start this problem. Whenever we are solving the problem of SFD and BMD, we will solve that in three simple steps. The first step is calculation of support reactions. Now, while calculating the support reaction, if we see here we are having a cantilever beam. In this cantilever beam, one end is fixed and the other end is free. So at this fixed end there are three types of reactions. Those are, first of all, horizontal reaction, which is called as horizontal reaction at A, HA. Then there is vertical reaction at A, which is called as RA. And then there is even a moment reaction which is at A, moment at A. Now, what are the meanings of these reactions is, because of the horizontal reaction, this beam cannot move in horizontal direction. Because of the vertical reaction, the beam cannot move in the vertical direction. Next, because of the moment present here, this beam cannot rotate. So whenever we have fixed end in a beam, at that point we have three kinds of reactions. Now, by looking into this beam diagram, I can say that there are no horizontal forces acting on the beam. We only have vertical force of 3 kN, 2.5 kN and UDL of 1 kN per meter. There is no horizontal load, so this horizontal reaction HA will be directly equal to 0. That is, the value of horizontal reaction at point A is directly equal to 0 since no horizontal forces. Now I'll calculate the vertical reaction. For that I'll use the condition of equilibrium, and that is summation of Fy is equal to 0, where my convention is upward forces are positive and downward forces are negative. Now, by looking into the diagram, I can say that RA is the upward force, reaction is in the upward direction, so this will be positive. So we have RA. Then 3 kN is acting downward, so negative, and 2.5 is also downward. So minus 3 minus 2.5. Next, UDL is there for a length of 2 meter and its value is 1 kN per meter. So 1 into 2, that will give me the value of load. So it is, and that load will be acting downward. So minus 1 into 2 is equal to 0. So therefore on calculating, I'll get the value of RA as it comes out to be 7.5 kilonewton. This is the value of the vertical reaction. Next, I'll also calculate the moment. So taking summation of moment of all forces about point A, and here my convention is clockwise moments would be treated positive, anti-clockwise would be treated as negative. So by looking into the diagram, this force of 2.5 kN is producing clockwise moment at A. So it will be 2.5 into this total distance, which comes out to be, that is 5 meters. So plus 2.5 into 5. Next, 3 kN is also producing clockwise moment, so plus 3 into 1. Then there is UDL. This UDL will be converted into point load, that is 1 into 2. So first 1 into 2 that is I have converted UDL into point load. Next, if I convert the UDL into point load, that load will be acting exactly at half of 2, that is it will be having value 1 meter from point C. And next, if I take the distance from A, that will be 1 plus 1.5, that is 2.5 plus 1, it is 3.5. So into 3.5, and it is producing clockwise movement, so positive. On calculating this, I'll get the answer of bending moment as it is plus 22.5 kilonewton meter. Now this is the reaction bending moment. It means here I am getting the moment in the positive direction, that is a reaction, but the moment produced because of the forces will be in anti-clockwise direction. So here, after this, I can say that step number 1 is completed. Next, step number 2, which is the shear force calculation. So here we have step number 2, in which I'll calculate the shear forces, SF calculations. Now for SF calculations we require sign convention. So here I am writing that sign convention. If a force is on the left hand side of the section acting upward, if it is on the right hand side of the section acting downward, both will be treated as positive. Next, if the force is there on the left hand side acting downward, on the right hand side acting upward, both will be treated as negative. So here I'll find the value of shear forces, and for cantilever beams we will always start calculating the shear force from the free end, because if we move from free end to the fixed end, the shear force value will go on increasing. So that first of all I'll calculate the value of shear force at point E, and for that I will take the section just to the left of E. So when I am taking this section, on the right hand side of E we have downward force, so any force which is there on the right hand side of the section, that is positive. So therefore SF at point E, it is equal to plus 2.5 kilonewton, the shear force value at point E. So now here I have calculated shear force at point capital E. Next, if we see between point E to D there are no load, so the value of shear force will remain constant up to point D, that is to the, if I take the section to the right of D, then up till here the shear force value will remain constant. So SF at point E and SF at point D both are same. Even if I take the section slightly to the left of point D, then also the shear force value will remain constant. So I'll write down SF at point D is equal to plus 2.5 kilonewton now. Then I'll calculate the shear force at point C. So SF at point C will be equal to, when I keep the section at point C, on the right hand side of C I have 2.5 kilonewton acting downward, so that will be positive, that is plus 2.5. Then I have this UDL which will be converted into point load, so it is 1 into 2 acting downward, so positive, that is plus 2. So this gives me the shear force value as plus 4.5 kilonewton at point C. Then this value of shear force will remain constant from C to B up till I can say that to the right of B this value will be constant. from C to B, the value will remain constant because to the right of B there are no load present. So therefore shear force at point B is equal to, now this 4.5 will remain constant up to the right of B. Then if suppose I take the section to the left of B, so on the right hand side we even have this 3 kilonewton force which is acting downward, so that will be up till the right hand side, that is 4.5 plus 3, that is plus 7.5 kilonewton. Now this value of plus 7.5 kilonewton will remain constant from B to A because there are no loads present between B to A. SF at point A is plus 7.5 kilonewton. It means if I take the section to the right of A, then the shear force value is plus 7.5 kilonewton. If I take the section to the left of A, then on the left hand side of this section there are no forces, so shear force value will finally be 0 on the left of A. Now once I have got all the values of shear forces, I can plot the shear force diagram, and for that I'll have to draw the beam again. So I am drawing the beam diagram again, and below that I'll draw the shear force diagram. Now I'll plot the shear force diagram. For that, first I'll draw a horizontal line. Which indicates 0 shear force. It is 0 kilonewton. Then the shear force value at point E, it is 2.5 kilonewton. This value will remain constant from E to D because there are no forces between E to D. Next, at point C, the value is 4.5 kilonewton, again positive value. Now between C to D there is UDL, so shear force will be an inclined line. Whenever there is UDL on the beam, shear force will be inclined. Here the shear force diagram is an inclined line. Next, between C to B there are no forces, so this 4.5 will remain constant from C to B. Then at point B the value of shear force is 7.5 kilonewton. So from 4.5 it will go on increasing and reach a value of 7.5 kilonewton, and then at A also it will remain constant as there is no shear force from B to A. So it is 7.5 kilonewton, and after that it will return up to 0 because there are no forces to the left of A. Here this diagram is positive because it is above the line. So this is the shear force diagram, and here we complete step number 2. So now after completing step number 2, that is the shear force diagram, we'll go on to step number 3 for bending moment diagram, because bending moment diagram will be just below this shear force diagram. So I'll write down the step number 3. It is bending moment, that is BM calculations, and in that first I'll start from the free end, that is moment at point E is equal to 0 since it is free end. Here if we look at point E, as it is a free end, so whenever the load comes this end would bend. So here the bending moment at point E is equal to 0. Whenever there is a cantilever beam at the free end, the bending moment we have to take it as 0. Next, bending moment at point D, that is moment at D, is equal to, for that I'll show the convention first. Now, clockwise moment on the left side of section, anti-clockwise moment on the right side of section, both are positive. Then anti-clockwise moment to the left of section, clockwise moment to the right of section, both are negative. So by using this convention we are going to find the bending moment. So therefore moment at point D will be equal to, this 2.5 kilonewton is producing clockwise moment at point D and it is on the right hand side of point D. So to the right side of section clockwise moment is treated as negative, so that will be minus 2.5 into 0.5, and the answer is minus 1.25. Unit will be force into distance, that is kilonewton meter. Then moment at point C, here for the calculation of this moment, on the right hand side of C, 2.5 kilonewton force will produce clockwise moment and the distance is 2.5 from E to C. So that will be moment at E is equal to minus 2.5 into 2.5. Moment at point C it is, and then there is even UDL. This UDL value, first I'll convert it into point load, that is 1 into 2. So 1 into 2 UDL is converted into point load, and the distance of that point load will be acting at half of 2, that is 1 meter from point C. So when I take the moment, the distance is 1 meter, that is half of 2, and it is producing clockwise. So on the right side of the section clockwise moment is negative. Therefore, on calculating this, moment at point C will come out to be minus 8.25 kilonewton meter. Then moment at point B, for this again on the right hand side of section 2.5 kilonewton is producing clockwise moment. The distance is 1.5 plus 0.5, that is 2 plus 2, 4, so that is minus 2.5. Moment at point B is equal to minus 2.5 into 4. Then this UDL into point load, so 1 into 2. Now this UDL into point load, that converted into point load, it is acting at 1 meter from C, but from B the distance is 1.5 plus 1, that is 2.5. So into 2.5 meter distance, and that is clockwise moment on the right hand side, so negative. So from this I'll get the value of moment at B, which comes out to be minus 15 kilonewton meter. After that, moment at point A is equal to 2.5 into the total distance, which is 5, producing clockwise moment on the right hand side of A, so negative, minus 2.5 into 5. Then this UDL into point load, so that is 1 into 2. Now that point load will be acting at half of C, so it is 1 meter from C, but the distance of that point load of UDL from point A will be 1 plus 1.5 plus 1, that is 3.5. And since it is clockwise, so negative, then 3 into 1, again on the right hand side clockwise moment is negative, so minus 3 into 1. From this I'll get the value of bending moment at point A. Answer is minus 22.5 kilonewton meter. So these are the values of bending moments. Now after getting the bending moment at each and every point, we can plot it onto the bending moment diagram, and just by looking at the values of bending moment, I can say that all the bending moments are coming out to be negative. First I'll draw a zero line like I've drawn for shear force. This is 0 kilonewton meter at the free end. Here this is zero line. So at first point D, moment at D, that was minus 1.25, so minus means it is below this zero line. 1.25 kilonewton meter. I am just writing the value first, later on we'll give the sign. Then at C it is minus 8.25, so again minus means below this line. Then at B the value is minus 15, and at A the value is minus 22.5. Now I have to connect these points. As from D to E there is no load, so this shear force was a straight line, bending moment will be an inclined line. Then between C to D there is UDL, so shear force was an inclined line, bending moment will be a parabola, and this parabola will be in such a way that it should give the value maximum at 8.25, that is, it should go on increasing from 1.25 to 8.25. Then after drawing this, from B to C again there is no load, so shear force will be an inclined line. From B to A there is no load. Here shear force was I can say that shear force was a straight line, bending moment is an inclined line. Remember, from B to A, here again there is straight line in the shear force diagram, so there will be inclined line in the bending moment diagram, and finally the value will be 0, that is there is no moment on the left hand side of A. So here this will be negative. So this is the bending moment diagram, where I'll write down that there is parabola from C to D, and once we have completed the shear force diagram and bending moment diagram, we can say that the problem is completed.